So last year I was here and I talked about some very simple algorithms for recommendation. And they're called puppies and ponies kind of colloquially because of the illustrations that I use. But today what I want to talk to is how these methods can be adapted for honest-to-God real-time use. And the results are good. They're real-time. They have strict bounds on the computational complexity. And so they really are honest-to-God real-time, not what a lot of people say is real-time, which is kind of sort of pretty fast. So my name's Ted Dunning. I'm Chief Applications Architect for MapR. I'm also PMC and early committer on Apache Mahout. Apache Mahout is a machine learning library that started on MapReduce, has recently moved to use Spark and H2O as computational platforms. And many of these algorithms are available there. So the background here is what I'm going to talk about first, how puppies and ponies actually works. The basic idea is that we use co-occurrence learning and drive what are called indicators into a search engine. The search engine is used to deploy the recommenders as opposed to a purpose-built recommender. That has lots of advantages. I'll talk about them. Then I'm going to talk about some of the tricks that are used to make puppies and ponies strictly scalable, meaning the computation is proportional to the number of users you have. That allows it to be completely practical for a lot of small teams or even large teams. Then I'll show some accuracy tricks for how to make things run better and then how to move to real time. So we start out. The basic idea is that you take the history of what people have done, and that's the upper left matrix here. On the rows, we have labels which are people, Alice, Bob, Charles. And on the columns, we have things they might want, things they might buy, things they might relate to. We transform that matrix into co-occurrence. Co-occurrence now has, of course, items on rows and columns. We've lost the users because we're averaging over all users. And then the last one, we transform to indicators, which are the significant co-occurrence. Let's talk about how this happens. First, the input, the history matrix of what people have done, I'm going to talk about as A. The co-occurrence, strictly speaking, is just A transpose A. For each row in A, for each person, find all the pairs of checkboxes that appear and emit that pair and then count them. Use them as indices in the co-occurrence matrix and accumulate those. That's what the operation is. It's easily implemented in MapReduce or in Spark, and that's one of the attractions to this. This basic operation is the heart of puppies and ponies style of recommendation, and you can now see, by the way, the puppy and the pony up there. And then the next step is we reduce the co-occurrence matrix to what we call significant co-occurrence or indicators. And then those indicators, each row becomes a field in a retrieval document. A transpose A becomes sparsified using a test that I'll show in a moment. So the basic idea from the user's point of view is, so Alice comes in with an apple and a puppy, Charles walks in with a bicycle, and Bob walks in with an apple. What are we going to recommend to Bob? Clearly, out of this enormous big data, this is a big data conference, right? So here's my big data, 3 samples. It's not funny. I actually built a system once, and we had to go into production a little bit before the data acquisition was ready, so we had 12 data samples to start with. That was tense. That was tense, and we got lucky. It worked. But anyway, so Bob got an apple. What else would Bob like? Well, of course he wants a puppy because that's what Alice got, and she had an apple too. So that's the similarity we see between Bob and Alice. Now, Bob also wants a pony. Who here would like a pony? Or at one time, yeah, I thought so. Everybody likes a pony. Or at least thinks they want a pony before they get a pony. And the reason that so many people still want a pony is because they didn't get one. Some of them are mean. So these are nice ponies, though. And so if everybody walks in and gets a pony, what are we going to recommend or expresses interest in a pony or whatever? What are we going to get for Amelia here? because she's just like Alice, as far as we know, just like Bob, just like Charles. So the fact that if everybody gets a pony means pony doesn't indicate anything except this is a person like everybody. We might as well just recommend the most popular things to a person who has a pony. So we have a problem here. Very popular items co-occur with essentially everything. And so widespread co-occurrence is not interesting for indicators. What we want is anomalous co-occurrence, not simply frequent, but anomalous, more than we would expect. We would like to get those useful indicators from log files via co-occurrence and testing for anomaly, and then we can push them into our search engine. Here's an illustration of how this detection of anomaly works. This is based on a test that I could say I developed it, but in fact I rediscovered it many years ago. And it's been used all kinds of places for finding anomalous co-occurrence in different domains. In the upper left example, A and B co-occur 13 times. B occurs without A 1,000 times, and A occurs without B 1,000 times. So if we just look at the first column, A occurs 1%-ish of the time with B. And then we get non-A things. So B occurs roughly 1% of the time in the absence of A. That means B occurs at about the same rate, whether or not A is there or not. This means that's uninteresting. In the upper right, on the other hand, A and B only ever appear together. Oh my God, it's a coincidence. It's what, but there's only 3 data points, like in the earlier example, so this is not interesting because of lack of data. Lower left is more interesting. A and B only occur together once, just like the upper right, but they're both relatively rare, and we have more data. So it's at least kind of a 1 in 10,000 sort of thing that the only time we ever saw them, they were together. If 2 people walk down the street that you've never seen, and they're walking right next to each other, you see them co-occurring, you go, maybe there's a connection. It's not a strong inference, but it might be. If, on the other hand, you walk to lunch every day, and you see the same 2 people walking next to each other 10 times in a row, and you never see them apart, you go, wow, something's going on there. There's some mechanism that's bringing them together, either themselves or some external influence. And so we will put scores on this, and the root log likelihood score is roughly like standard deviations. 4.5 is almost good enough for a new subatomic particle, but of course we knew which particle we were looking at, whereas we're looking at millions of possible pairs, so that's not very interesting. Only the 14 is really very interesting. That's kind of a 1 in 30 million sort of chance to get that. So that's what we do. We reduce these co-occurrences. We have a search engine, and the search engine has in it, here we've got metadata for a puppy, the sort of thing you would have in a search engine if you were searching for puppies. And we take that row of indicators for puppies. It has only a check mark with apples, because that's the only significant indicator, and we slide it in as an indicator for the puppy. We can now search not only with text, but with behavior. If somebody comes in, like Bob did, with an apple, we can do a search for folks with apples, tended significantly, interestingly, anomalously to like puppies. We can search with behavior. It's a search engine still, but because it's searching with behavior, it is now a recommendation engine. This is puppies and ponies. It's not difficult. The core of it is the co-occurrence computation. You can view it as a self-join. You can write it as a loop for each user, take all pairs of things that user did, and count those pairs. You can write it in lovely Greek letters that makes you look fancy. You could wear a red hat if you do that with the special black belt edition. But there's nothing really special about any of these things, except the last one is very few symbols, so we can think about it perhaps more efficiently. We can manipulate those symbols. But A transpose A is the core of that co-occurrence computation. Now, we can do a little bit more than that. We don't have to have A against itself. We could have two kinds of behavior. We could have watching a video. That's the thing we'd like to recommend for people because they might want to watch a video. But we might have some other behavior, like opens the description on something or types in a word of text. Those are other behaviors that we would like to use as indicators for the one we want to recommend. So in that case, we can do cross-occurrence. It's just the same. For each user, take an element from A and an element from B, form the pair and count those. But we're crossing now from A to B. For all combinations of A to B, we count them, not just A to A. Following along the Greek letter trend, it's very fashionable apparently in these slides. There's A transpose B instead of A transpose A. It's very simple. If we were to adjoin A and B, then we could express that same sort of thing as a self-recommendation, a co-occurrence in that adjoined matrix. And you can see that the co-occurrence terms appear on the anti-diagonal of the block result. This is kind of all of the kinds of co-occurrence of A, co-occurrence of B, and cross-occurrence of A, B to A, and A to B. So all of those form in there. Now, this is cool. This is fun. But it's not good enough. The reason it's not good enough is because of the cost of the algorithm. So we have a problem with scaling. And the problem is right there. If we look at how many pairs we're going to get, if we have k sub I things in a row I, we're going to have k sub I squared over 2 sort of pairs. Squared. That's the kiss of death. That means not scalable. And so what we can do, and these are pragmatic ideas. These are not theoretically well-defined ideas, other than the idea that if we've seen 1,000 DVDs that you've looked at, or 100, we probably know what you like, especially if they're the most recent ones. Or if we've seen the last 600 songs you've played in your iTunes, we probably know what you like. We're not going to learn much from the 601st song, so we can downsample everybody's history to some reasonable proportion. 100, 200, 500, depends on your domain as to what is a reasonable thing. 300 to 500 is something I've never seen cause any visible effects, so that's a fine suggestion there. We can also downsample all items so they have a maximum frequency, the maximum number of users who have ever interacted with them in our downsample data set. What this does is it takes a very, very popular item, say the intro video on your website that everybody has seen, that provides us with no information. And so rather than pay the cost of doing co-occurrence on that, we downsample it to about 1,000 people or 500 or something like that. Now the first one affects mostly QA teams and bots, both pathological types of people. The second one affects mostly ubiquitous elements in the data stream, and those are also pathological and not usually what we want to recommend. So in both cases, the downsampling affects the things we don't care about. But more importantly, in Sebastian Shelter's work, he showed there was effectively no difference anyway for anybody. So this is a good thing to do. The reason it's good to do is because that k squared is now bounded. The number of non-zeros in any row is at most k max, whatever our interaction cut threshold is. And that means we have an absolute bound, and now the computation is linear in the number of users. There is a bound on that. And furthermore, there's an average which may grow faster than n, but with the bound, we have a bound on that as well. And that means the total time that we have to spend without the cut is quadratic and is strictly unscalable, meaning bounded above will not be as good as order n. And downsampling makes, at worst, order n. This is big news. This is what makes these algorithms highly scalable. I was first did these things, this is back before we understood what we were doing, and we were able to handle 250 billion observations on Hadoop machines in 2009. A dozen machines. And they were not the best machines, I'll tell you. They were the ones nobody wanted. So here's the benefits. Even on a small data set, this is on the million song database. There's 48 million observations. That's user song pairs. And they're in triples because they have a count on them. I throw away the count because I don't care. And without downsampling, we have about almost 6 billion pairs that we would have to count. And with a reasonable amount of downsampling, we have about 1/10 that number. And the effect, though, on larger data sets, remember I just mentioned that I was working on a system that's 1,000 times bigger than this on a very conventional website. The upper thing, without downsampling, is quadratic and rises quadratically. The other ones are bounded and rise linearly. So the ratio, the speed up of this downsampling, becomes greater and greater, roughly order n. So roughly, with 1,000 times more data, we would see that ratio be 1,000 times larger. This is a big deal. And you can see that the effect of the interaction cut has little effect on the computation speed for a particular frequency limit. Now, the batch scaling in time, the fact that the batch algorithm takes order n time, implies that the co-occurrence matrix that it produces is limited to order n in space, because it doesn't have time to do anything more than that. And that means we can put bounds on the size, very tight bounds with this downsampling, on the size of that co-occurrence matrix. This is the zero norm, so it's just the sum of all the non-zeros. But we can do more than that. The idea here is that the batch co-occurrence is order n, and we've processed n users. The question becomes, can we process a new transaction in order 1 time? The amortized time is good enough. Is the instantaneous single transaction good enough? Now, if we were going to use a matrix factorization, that's the other major branch of recommender technology, is to factorize that A into item and user vectors. If we were to do that, then it's very difficult to bound the size of that update. All kinds of things could change. But with this, we have a chance because it stays sparse. The sparsity lets us bound that update. And co-occurrence is a very accurate recommender at large scale. Factorization is good at small scale, but what we're worried about here is the large scale. So we have this fortuitous co-occurrence. So let's do that. We want, if we're going to have an online algorithm, each unit of input has to give us order 1 work. That's the theoretical bound that we have to satisfy. We also have to have small enough constants that on average, the amount of work that we have to do is feasible. It's a pragmatic constraint. And also, the total accumulated data must be small enough. We already have that bound. So it's the middle bound that really is the most important. And we, of course, need the theoretical one if we can get it, but I'm always happy to settle for pragmatic bounds. So we want to take, this is a block diagram built for a customer at one point, and the idea is that the original system takes item metadata, puts it in a search engine, it takes log files, pre-processes them into suitable form, it does batch co-occurrence, post-process them, and sticks them in as indicators into the search engine. Sorry, I couldn't read that. Could you show me again? 0, 5. Well, we're going to have to talk fast. Here we go. And then the web tier does the search. We, of course, are only worried about the batch co-occurrence thing. We want that to be real time. We can put a space bound on that, and that will give us a time bound. Because user histories are pruned, we know that there's a finite size on that. That's twice the interaction cut. if we look at what happens, what we're doing here is adding one interaction between user I and item j, that's A plus EIJ, to this co-occurrence matrix. And then I'm going to subtract away the old co-occurrence matrix. This tells us what changes. If the size of that is bounded and tight, then we win. And if we look at it, if we do all those multiplications, it turns out that we're going to put one row in a bunch of zeros and one column in a bunch of zeros beside it and one additional element. That row is exactly the previous history of that user. It, of course, has k-max elements at most. So the update here has k-max elements in the left one, k-max elements here, and one more. But in each of those three, one element is in common, so there's 2k minus 1 work that's necessary. This is the strict bound on this, which says this is order 1, because that's a constant. It gets better, though, because every new observation may, in fact, have been pruned. It may not have actually been interesting. It might have hit the frequency limit, or it might have hit the user's cut limit. And so we could probably ignore that a lot of the time. And in fact, on the million song database, half of all the new updates are prunable. Also, on average, k is much less than the bound. That means for the million song database, the average typically is kind of like a log of the size, and the LLR cutoff makes the counting almost the entire load. Very rarely do we actually update the retrieval index. So here's how that grows. You can see with the interaction cut, the size that the average increases only slowly. Here you can see a log fit to all of 3 data points. You can see that the frequency cut increases the average, but only logarithmically, and it's much, much smaller than the cut, which was hundreds. That means it's much, much faster than our bounds, but still bounded. So, recap. Co-occurrence-based recommendations are simple. You can deploy them almost no matter who you are on a weekend with stuff you find around the house. You can put it on a Raspberry Pi if you like. It's easy. You laugh. Somebody's done that. I won't say who. You can also do this interaction cut and frequency cut, and that's the key to scalability, both in batch and real time. The same things that give us the bounds in batch lead to the same bounds in real time, and fully online recommendation is not only feasible, but it's easy. And that's what it's all about. You can find a book on rep puppies and ponies, appropriate given the cover, online at the MapR website. We have a book similarly, it's a little tiny book, on a simple idea on time series database at the MapR booth. I'm Ted. You can ask me questions anytime, except probably right now. Other than that, anytime. And I encourage you to check out these other projects as well. Drill, Mahout, and there's a new one coming, Kylan. I just signed on as champion for that. There's a lot of stuff happening at Apache.